All right, let's start. So welcome to the training on MZmine GNPS, feature-based molecular networking. So as you're probably aware, Ming created a new documentation for GNPS, and the idea is to couple the training with like the documentation. So that's why I just emailed you a link for the new GNPS documentation, where in theory you should find all the information we talk about today. So yeah, if you want to open it and have already a look at it, then I send you a second email with just like a MSV ID. So that's a massive ID, basically for a test data set we can download and work with today. So in this data set, basically all files and information is contained, which we need for today's training. So yeah, for the structure, we're first going to talk about how to get data and put data onto Massive through an FTP client. Then I'm going to show you how to pre-process that data with MZmine. That's a feature finding tool which I would use. Then Ming will show you how to create a molecular network combined with like the quantitative or semi-quantitative information from MZmine with a new GNPS workflow. And then we will follow up a little bit on visualization of this information in Cytoscape. So these are basically like the three elements. I also send you links for software to download. I know there was some problems with downloads of FileZilla. So apparently the latest version of FileZilla triggers like a security alert in some of the antivirus software at UCSD. So right now, if you have not downloaded it, I would not encourage you to download that. Did you get that links?
Yeah.
Okay, but you didn't have problems?
No, I don't think so.
Okay, that's weird. So maybe you downloaded it at home also. So
yeah,
it seemed to be like a problem.
I just had to update my JavaScript.
Okay. So anyway, so I have like right now only FileZilla installed here, so I'm gonna use it, but you probably want to discover other FTP clients.
If you're in Windows, WinSCP is a good one.
Okay. We can maybe send a link for that.
We'll send it
Later. Okay, so I'm gonna log in right now on the one of the data analysis computers, which I'm remotely connected to, and then we're just gonna start with like pulling this massive data set. Okay, and so if you want to first get some information about that, you can just like open your browser and then go to massive.ucsd.edu, and if you go here to access public datasets, browse publicly available datasets, you can search by this massive number I emailed you. So if you take here this number, okay, Justin can't hear us. So my microphone is not muted, so you should be capable. Can you hear it with the headphones?
Let me check. I did earlier, but let me check again.
All right, so anyway, if I copy the massive ID here in the title and then just hit filter, then there should be just like one data set popping up, and that's GNPS feature-based molecular networking workshop. So yeah, Louis was so kind to create this data set. And now you can like click on this, and then basically you get some basic information here, what is in there. And then you see also that here is an FTP link. So you can either open this and like manually download all the files in there, but I think that's not really elegant. So I just take this and copy this link. And then I would go to FileZilla or any other FTP client, and I just paste this into the host field here, and I hit quick connect, and okay, let's abort previous connections and create these new ones. And then you can see here on the right side that I see now all the folders which can be found under this FTP link. So if I go back to the browser where I just was, if I click on here, you know, I see as well like the same folders. And if I go through, I can like reach like all the files, but it's kind of like inconvenient to now download them all manually. Otherwise, I can also use FileZilla to upload stuff later. So it's a really convenient tool, probably the same way as other FTP clients are. However, what I need now is basically the peak folder, because here are all MZXML files. And you can see when you go a little bit into this, there's 2 folders, 2 plans or less, and 30 plans or more. So right now I would just encourage you to download these 2 folders, because these are like the initial files we're going to use. So then besides this, if you go higher, you can go to other, and there's a metadata table. This you will need later for the network job submission. And then there's also folder updates, and Louis uploaded yesterday also a batch file for MZmine, as well as the already processed files. So in case you kind of drop out during the MZmine pre-processing, you can go back to this folder and basically just like download all these files, and then you get like already the processed stuff in order to continue later for the networking and so on. Okay, so yeah, maybe download already the Qtov batch AG training file, because there are some settings, so this might be helpful for the MZmine part. All right. So if you manage to download all of this, then yeah, you can go ahead and open MZmine. So you all installed this yesterday and it's running, I hope, or you have it from previous usage. And then, yeah, when you started, you should see this window here. So now you have basically 2 options. This is first, you can like do the processing step by step manually here with the graphical user interface, or you can upload a batch file and basically process all the files in a batch mode, which I think for like the later use, when you do a lot of data analysis, is the more convenient thing, because it's just like fire and forget, and when you come back the next morning or so, it's all processed. But I think for like educational purposes, it's good to go through step for step, especially if you're not sure about like the parameters, because there's a lot of like graphical possibilities to assess the processing you did. So hence, I would just say let's go through this manually. And if you want to redo this later, you can also use the batch file. I just showed you the location. So if you want to do so, then you would go to project and batch mode, and then just like load here this batch file we just talked about. Thank you, that's so nice. Okay, so then if you have a batch loaded, then you see here basically like the different modules we're gonna apply for like the processing of the data. And then when you click on configure, you can basically change the location of the files, mass detection limits for the peak picking, and so on. But I'm basically gonna talk with you about each function which is already in this batch when we go through manually. So just like to give you like an overview of the structure of the graphical user interface. So here on the left side you have raw data files. So right now there is none, and on the right side there is peak lists. There's also nothing right now, but like the first thing is we load up raw data files, and then they should appear on the left, and then as we process them and create peak lists on it, then they should appear on the right side. So in order to get like the raw data files, we go to raw data import, and then browse to the place where you downloaded the MZXML files. So I already copied them here in one folder, so I can mark them all at once. So you would have to go first to 5 plants or less, upload them, and then 30 plants or more, and then load them. And then however you just hit open, and then yeah, you can see it loads them into the program, and then I get my, I don't know, 30 files or so here on the left. So everybody managed to open MZmine and have the files in front of him.
No, it's not working.
You just got stuck with like downloading the data.
FileZilla. Yeah,
Okay.
mine is just rejecting it. And then
Can you go back to the massive page?
this one?
Yeah, and I'll copy this link. Yeah. And now the information is here. So now
Oh, yeah, just
click it to peek. Yeah, and now you can download this folder.
I tried to.
Yeah. Can you just like drag and drop it on your?
I don't think that's.
And then, yeah, you don't do the MSV, you have to do the FTP.
No, but now it's. Yeah. Oh, okay.
When I try to do this, it just.
Problemet het afzien voor de laptop.
Okay, that's good.
Ja, de telefoon van toenemend.
I mean, it's fine. I can just follow.
Yeah, and then you can continue with the backup files.
Yeah.
Which you can like then download just through the web interface.
Yeah.
Alright. Well, did you guys manage to download the stuff? That's our studio downloads. Then maybe you can just like work together with me. You good? Awesome.
The other thing is go back to
Basically, it says there's this one. This is right.
copy that again.
Oh, no,
Like
it's
that.
just drag. Exactly.
Like,
So
I just drag and
So
drop
then
these
what we
over
should
here.
probably have is the camera closer.
And now
Either-
it's,
It seems like
It should be significantly less.
right across. We're zoomed in. No, like next time, like have it
How do I
down.
get out?
Next, like,
I'm like worried I'm
oh, but it needs to. Yeah. Well, I can. But then we're getting the audio. Well, the audio's from this. Oh, okay. Whenever the audio wants, it's like very definitely. So perhaps if when doing the little like tutorial sessions, if like he's gonna go around and like, or you guys are gonna go around and help people, then just like put a microphone on you. So
it's a very long time.
oh,
I can be
browser
something
when
when
everybody was
it's
talking.
like-
It's just like,
Oh,
okay. Yeah.
Transfer them down from the phone.
Yeah. Just initial feedback. I think well, ideally what I want to do is I want to get a trick and I don't know, mic stand and then have a boom mic. Just wait, yeah. Well, I can do it. I have the equipment. Of course, you have a boom mic. Can you? Yeah. Or at least like it'll sound really right.
double click.
Right click. The problem is like they compress the audio so much. Oh yeah. So I want to stop and move whenever I actually do it. Okay. It's like you.
So when I browse to your
I don't see it. I want to try and put them on my desktop.
Yeah. Where can I find your desktop here?
It's right here.
Okay.
But you probably have
So I think it should be really.
You can't write
Sometimes
the
my,
volume.
this
just
happens
like-
on my computer multiple times. Yeah. That's what I usually
You guys put on, where do you want to put on your computer?
Now it's 22 files.
Okay.
That looks better.
And then Daniel's having problems getting files as well. We tried.
Okay. So did you get it?
You write to, I don't think you write to home.
When you open FileZilla, did it tell you to upload?
Yeah, I don't think you write to home.
No,
you
actually,
put it
it's
on
not.
audience.
Because that was my issue. I just fixed it.
No, user
It's
too.
not letting me out.
Okay, great. So I think you did not copy
Put it on
the
desktop.
link. So if you go to display
Yeah, right there.
and then go here.
Oh, we can disconnect it. Yeah. Are you on this? Maybe they kicked you off there.
See now. Oh,
There you go. Yeah. You just can't write. It's a max. So
You go to later on. But you're Brazilian affiliation.
Are you a guest?
Yeah,
Oh, yeah.
that's why.
Yeah. You get unprotected or you don't have credentials?
I think I need the email from the university first.
Oh, okay, yeah.
Yeah,
You won't be able to unless it blocks the port. So,
But try Illuron. And this is like your Brazilian login. Just use as a username your Brazilian email address.
okay.
And then you, as if you would log in at your home institution. Normally, I think it must be your university email address, not your Gmail.
No, thank you for
Okay.
it's that one.
Yeah, try it. And if not, you can then just download through the web interface, the processed files, and then you can just follow up, maybe work together with Julia.
That's okay. I just tried to download it, but it didn't work.
I brought it in for. You have to go into and click the MZxML files literally. All right, so I guess at least some of you managed to grab the data. There's some internet problems. Then if you cannot connect, then just work with your neighbor and then later continue with the other files we provided. So once you have the raw data in your MZmine window, then the first thing we do is we peak pick MS peaks in both MS1 and MS2 data. And when you go now to the documentation I sent you earlier, then you can basically find a similar step. Let me just pull that up. When you go to experimental data analysis and then feature-based molecular networking. So when you click on this, then you basically see an entire protocol with like 10 steps for importing, peak picking, chromatographic deconvolution, and so on. So in case you get lost with what I show you right now, you can just go back to this documentation and it should be very clear. Important, if it's not clear, then let us know, because this is just like a, I guess, a beta version now or so. So we're still updating it and improving it. I think especially Ming will be happy for that feedback. All right, so yeah, going back to my MZmine window. So as I said, the first step would be raw data import. So now we have the raw data, and now I perform peak picking. So therefore, I go to raw data methods, peak detection, and then mass detection. So I already did some settings here before, but I'm just gonna remove this now and start from scratch. So yeah, for this training, I kind of assume that you all know how LC-MS data is structured, and that we have MS1 and MS2 information in data-dependent acquisition experiments. So as we have MS1 and MS2, we need to peak pick both, but they have like different signal to noise ratios, so hence we have to set different thresholds for MS1 and for MS2 data. So now the question is, what are those thresholds? And so when you're an experienced user with a certain type of machine, for example, like the Q-Exactive, then you know, okay, that's like the generic threshold to set. But sometimes, especially if you're new to it, you have like no idea. And then the cool thing here is that you can just like preview that and kind of get like a visual hold on what is an appropriate threshold. So first of all, I'm gonna go and set now a filter, because in the first round, I only wanna do MS1 level. So therefore, I go to set filters, then MS1 level, set 1, and then OK. And then the other thing I have to do is I have to select the mass detector. So here we're working with MZXML files, so they are already picked during transformation. So hence we do not have profile data, we have centroid data. So here it's already correctly selected, centroid. If not, I can just redo this. And then on the right of it, I can set a threshold. And here, okay, it's right now set to 10 to the 2, but I don't know if this is an appropriate value, right? So I can now click here, show preview, and then it maximizes this window, and I can basically select now different raw data files in my set and go to like random scans somewhere in the middle of the chromatogram, and then toggle till I reach like an MS2 scan, an MS1 scan. So in this case, you can see, okay, here it's an MS1 at 4.459 minutes. And then all the red peaks are basically peaks which would be detected with the threshold, and like blue peaks are peaks who are missed. So with 10 to the 2, it apparently gets a lot of peaks in here. If we would have, for example, 10 to the 5, you know, that would be too high. So nothing would be detected. Hence, my product at the end would be like very sparse. So yeah, let's maybe go back 10 to the 2. But then when you like zoom in, you see that like also like peaks in a noise range down here are selected. So you eventually want to like increase this a little bit. So if we go, for example, to 10 to the 3.
So the threshold that I established will depend on my data set, right? That's it.
Mm-hmm.
Yeah.
Exactly. And this depends most strongly to like the machine you use. So because simply like the machines have different generic intensity values. So for example, there between like the QTOF we have here and the Orbitrap we have, there's like 2 orders of magnitude difference. That doesn't mean that this is more sensitive, it just has a different value. But yeah, so like going here with 10 to the 3 seems appropriate. So we get like most of the peaks and stuff like in a low intensity range is not detected. If I want to be very careful and like get as deep information as possible, I can go back to 10 to the 2, but be aware that the more peaks we pick, the longer the analysis time will take. So for 30 samples, this might not be a problem, but when you want to scale to like 1,000 samples, then an order of magnitude difference here will make a big difference. So yeah, in order to have it like fast done, I'm definitely going to keep the higher threshold now. So, and then I just define a mass list name. For example, here I call it test, and then I already provide like the threshold in this list, so I can remember and see what I've used. So this would be 1 E3, and typically we use like for MS2 1 E2, so I just call it like this. And then I have to make sure that like all raw data files are considered up here, and then just hit OK. And then you can see down here it does something. And once like the peaks are picked from a file, then you get like a little green hook over your folder here. Okay, so
Daniel, how did you get the little window for the parameters listed?
yeah, so I go to raw data methods, peak detection, and then mass detection. And then besides, next to the mass detector, there is this field, and then I can open here the parameters for the mass detection. Okay, and as we are here, now we do it for MS2 as well. So now I just clear the filter, oops, and set a new filter for MS2 level. Then I'll change the threshold accordingly for MS2. We can also give it another preview, and you will see if I go to MS2 spectra, yeah, overall the intensities are lower. So if I would have had 10 to the 3 here, there would have been only, I think, like 2 peaks considered. Yeah, so yeah, here you definitely want to use a lower threshold. Example values for these thresholds are also given in the documentation if you, even after inspecting them, are not sure about it. However, so now I have to make sure that the name of the mass list is the same, because it basically just extends like the first mass list we created with the additional MS2 information. So you just leave it, and then again hit OK. And now it's calculating again. Which hopefully will be done soon. How are you guys doing? Everybody got some peaks picked already? Here it's working, that's great. You guys are good? Awesome. Yeah.
Where was it in the documentation that it showed that?
So it's under experiment data analysis and then feature-based molecular networking. Maybe once this is like established, we can just like move it a category higher so you can directly access it, and it's not under experimental workflows anymore.
Or maybe under data preparation.
Yeah. And then yeah, it basically explains here step by step. And then yeah, here are already like 2 example values given. Okay, going back to my MZmine project. So now I can see that it's all done. So now I can progress with the next step. And the next step would be the generation of extracted ion chromatograms from these masses we just picked. So this is called chromatogram building in the software. Therefore, I go again to peak detection and then chromatogram builder. So here another window pops up now, and I have to basically select all raw data files. There is a filter already set. In case this is not the case, I want to set this to MS1 because our extracted ion chromatograms going to be built on MS1 level. And then I have to choose this mass list I just generated. So if you click to choose, then it provides you an option and you can choose that one. And then I provide a minimum time span. So in this case, I set it relatively short in case we have like very sharp chromatographic peaks. If you have like longer gradients or you do not have a UHPLC method, like very wide peaks, then you can like adjust this accordingly. Then I provide a minimum peak height per extracted ion chromatogram. And as we defined our initial noise cutoff at like 10 to the 3, I'm just gonna double or triple that, which would be considered like the limit of detection. So let's do 3, 10 to the 3, and then mass tolerance. So it will pick automatically like the lower value. So here I like to use a relative value, and for the Q12, 20 ppm seems to be like an like adequate value. For an Orbitrap analyzer or FTICR, that might be like lower, around like 5 ppm or so. Okay, and then when I'm happy with the settings, then I hit OK again, and then you see it starts building things, and now on the right side, peak lists start to show up. So now to get like a first idea, how does this look? I can just like double click on the peak lists, and then a big table pops up, and I have like this peak shape previews, which basically shows me how the XICs look. And then if you're familiar with, I don't know, like chromatographic separations, you can see some of them, like this one here, seems to have like a nice Gaussian shape, whereas others, like this one here, does not look like too great. So in the further process of the data, we try to get rid of these things and kind of like focus on the nice peaks. And then sometimes, like in this case here, you see that there are 2 peaks. So here we eventually have like a isobar, so isomer, which are 2 compounds with the same mass. They have different peaks. So those we need to split into 2. This is called chromatographic deconvolution, and that's the next step we're gonna do now in our processing. So fortunately, all my peak lists are made. So if I go now to peak list methods and then peak detection, I can go to chromatogram deconvolution. And then basically another window pops up with settings for this processing step. So yeah, first of all, I can select all peak lists, and then give them here a suffix deconvoluted. And then there's like an algorithm window, and here when you open this, you can see there's quite a lot of algorithms. So for example, Wavelet's algorithm from XCMS, there's local minimum search, and a bunch of other noise amplitude. I never tried that. And then baseline cutoff. So
How do I know which one I will use of that? Those?
So that just really like depends on you. So if you can like try different algorithms and see what performs best for your data. What I would recommend you is start with something simple and robust rather than with something very sophisticated. And I think like the most simple algorithm there is like the baseline cutoff. And then another algorithm I typically use is like the local minimum search. So this basically looks for local minima, whereas the baseline cutoff just like applies a baseline, and every time the signal goes beyond this line, it considers something as a new peak. Whereas like when you, for example, have like differences in like general like signal intensity, and like the minima between 2 peaks does not go below your initial cutoff, then like the local minimum search would be, for example, favorable. And if you have cases like that in your data which you like rely on, then you have like to try this out. But for today, I would just say let's go with the baseline cutoff, because I think it's really simple. So here we basically set here some settings, and it's just like a minimum peak height, which is basically like the same as we said before. Then we will provide minimum peak duration, So again, this depends a lot on the chromatographic separation you used. So here we had like, I think like a 10-minute gradient. So I probably don't expect peaks to be 10 minutes wide, right? So I expect them to be like sharper. And then I also provide a baseline level, which I will set for like the same threshold as at the beginning. And then to assess this, I think here again, the preview will really help us, because when you have to question, okay, what shall I use? You know, what algorithm? You can like just try this with like the preview. And then basically go through a bunch of examples. So in this case, you can see that this would be considered as a peak with pink color. And then there's the red one, which is a peak. So here it apparently does a good job, right? And I think that's like the strength of like the local minimum search. It does simple things very well. When it gets more complicated, it might not be super awesome. So here, okay, the main peak is considered, but the other peak not, probably because it's under our initial threshold. So if I would lower this now to 2, you can see, okay, then here this end of this hump here is considered. But as you can see before, the baseline like just had like a spike and dropped below the threshold, which probably was like not a real different peak, just like an interruption of the signal. So that would fall off. But overall, I think it looks okay. And I think when you do like feature finding of thousands of features, it's really hard to set this perfect for everything. So it's kind of like trade-off all the time. So yeah, I guess the settings look appropriate. So and I'll continue from here. And now you see that there's also another window here where you can check boxes. And this is MZrange for MS2 scan pairing. And then also a retention time range for MS2 scan pairing. And this is really important if you want to do networking with this data downstream. Because what this module does now is, after this deconvolution process, it takes the peaks, the deconvoluted peaks, and looks within a certain MZ and retention time tolerance, whereas there was an MS2 event triggered for that peak. And then it basically aligns this information and will provide you an MS2 scan for a feature. And this is the kind of like thing we rely on to do feature-based molecular networking. That's, yeah, pretty cool. So yeah, with the help from a bunch of undergrads, like, yeah, we here with Louis were able to basically get them, get this done to be integrated into MZmine, which I think was really awesome and facilitates our, or enables our entire feature-based molecular networking now. So yeah, here the settings basically depend also on the type of machines you use. So here I set 0.02 for mass window and then 0.1 minutes for retention time. Again, if you have like wider peaks and like longer gradients, then you want to like set this to like a more relaxed value. Also, if you would have low resolution mass spec data, for example, from a triple quad or so, then you have to adjust this mass tolerance accordingly. Okay, so yeah, I guess with these settings we should be good to go. And then process this again, and then you can see under my initial peak lists here, there is now a new set of peak lists which has the suffix deconvoluted. And yeah, now I can browse through, and I already saw like an example. So for example, this one here, you can see there's like still a double peak. So because they were not baseline separated, so here was the baseline cutoff. This is impossible to deconvolute them. So here, eventually the local minimum search would have done a better job. But overall, it looks fine. So, okay, let's open this again. And now I want to just sort this by retention time. And now what you can see is that when we go through the chromatograms sorted by retention time, many of those things have very similar peak shapes. So one of the reasons is there's natural isotopes of 13C mainly, right? So we typically observe here, for example, 476, and then a feature was 477, and then eventually one was 478 for like the entire isotope pattern. So this is of course redundant information because these are the same compounds, just the different isotopes. So what we want to do here is basically look for things with different chromatographic peak shapes and certain mass offsets, for example, 1 for like the isotopes, and then group them together. So to do this, I basically mark all the deconvoluted peak lists and then go to isotopes, and there's a isotope peak grouper. So now I again set this to values appropriate to my machine and to the chromatographic separation. And here provide the maximum charge, which is probably for metabolomics data not above 3. If you would have proteomics data, then you may want to increase that. Okay. And then again, hit OK. And then a set of new peak lists should be attached. And when we compare now, for example, for the file 10.23.2 P4, show peak list info. That's just a feature I learned yesterday, thanks to Ming. Then I can see that this is, has 692 rows or features. And now if I go to the same file, but deconvoluted one, then you see it's just 560. So it's considerably less. So of course, especially in the low abundant range, sometimes you detect only one isotope and not an entire pattern. But for most of the high abundant and high quality features, we should see more than one isotope. Hence, there should be like some reduction.
What about when you do isotope enrichment studies? How would you deal with that kind of thing? Would you leave them in?
So for example, if I would do like a full labeled experiment with like, I don't know, 13C sugar, right? Then I would not expect to have that isotope pattern. So then I maybe could like consider other isotopes like 15N or so to group them, but it's probably not as crucial as 13C because it's not as abundant unless you have other like weird heteroatoms as like halogens or so. But yeah, let's assume you just have like non-labeled data for now, and let's keep it simple. So once we have basically now also the files de-isotoped, now the final step here would be to compare them between samples. So we need to align all this extracted ion chromatograms between samples. So what I did now was all like sample centric, but now I basically want to compare between samples, and therefore I again mark all de-isotoped files here, then go to peak list methods, and now go to alignment, and I use the join aligner typically, and now I provide some mass tolerances in order to compare those different peaks between samples. So I set it to 20 ppm. I give it to like a weight of 75%, and then retention times 0.1. And yeah, as I trust my masses more than my retention times, I give it a lower percentage weight for retention time.
You have the retention time tolerance here at 0.1, and in previous steps also at 0.1.
Yeah.
Do you ever do the alignment a little bit like looser?
Yeah, you can do that. I think especially when you have like a large data set where you have like hundreds of samples and they were all run with the same column, then you would expect retention time shifts from like the first, for example, to the last sample. Then I would definitely relax that. So here, honestly, I do not know. So this is a subset of samples from a bigger cohort. We could just like put it to 0.2 if this makes you more happy. I'm happy to change this, but probably 0.1. So that would be 6 seconds, right? That's pretty wide as well. Okay, and then I hit OK. and now it fuses them basically together. And now I get on the very below like an aligned peak list. And if I double click on the aligned peak list now, you can see that I get basically multiple extracted ion chromatograms per feature. So this is like the aligned ones. And as you can like see here, so they look pretty much like the same. So I think if I right click one, I can show the extracted ion chromatograms in a larger window. Oh, but okay, it's only one. Okay, that does not look good. Oh, okay, because this is like basically the entire XIC and not the deconvoluted feature. Let's try for this. Okay, that looks better. And now when I can zoom in, if I zoom in.
How did you get the overlay there?
So if you go here and right click and then go to show and then XIC dialog, then this opens such a window here and then just hit OK. So, and then, yeah, I can basically zoom in. And now I see already like that most of the peaks had like a similar shape, but there's a bunch of peaks which have like a certain offset. So apparently there was like a retention time shift. But the difference is 0.001 minutes. So it's not too bad. It's pretty good.
No, that's MZ that you're seeing. The retention time shift we're at 0.1.
Oh, sorry. Zoom out. Yeah, I don't know if I can change the label.
But you can see it on the x-axis.
Yeah. Okay, so yeah, thanks, Ming. Yeah, so here the retention time shifts were
And that's the difference for the
0.1.
the apex of the peak?
Yeah. Okay, but anyway, I think this kind of like gives you like a lot of how I to visualize this. So for example, in this example here, there seems to be like a bigger retention time shift, but it was still captured. Yeah.
So that would be an aligned peak.
Yes. Yes. So here, because we set it to 0.2 after Julia's question, this has been captured. Otherwise, this probably would have been split into two different features.
Do you think they should be one feature?
I mean, it really depends, right? So if those two samples were like run after each other, then maybe not. But if there was like several hundred samples in between, I would not be surprised. A good way to assess this is to run like a standard, like in your first, like a QC standard in your first sample, and then compare it to one you run after your last sample and see what's the variance there. Okay, so when you now check the overall number of this aligned peak lists, then you can see it's 15,000 features. So this, although it would be not unexpected, for example, for DOM or for complex samples like the fecal samples here, a lot of those features are noise. So when we open the list again and scroll to the back, you can see that there's a lot of like things which are like really spiky, or I don't know, like a kind of hump, and they're only found in one sample. So those things you probably want to filter out. Also, what we want to filter out are things right now which did not trigger MS2s. So we're aware that this kind of like means that you will subsample your data set, but it reduces like the massive amount of information to the most high quality signals, and high quality signals where we have MS2, which we need for our molecular networking and database dereplication. So to do so, I basically do now some filtering, where I go to filtering and then peak list raw filter, and I can set now a bunch of different criteria. So for example, I can tell the filter to only allow features which occurred at least in 2 samples. So especially if you have like replicates, this is a very useful filter to use. So for example, if we have duplicates here, I say, okay, it must be found in 2 samples. Then another quality control are the isotope patterns. So yeah, I guess as we agree, like all carbon containing compounds should have like certain isotope pattern. So we can say, okay, only allow things where you at least have like 2 peaks in an isotope envelope. And then at the bottom, we can also say keep only peaks with an MS2 scan. So if I name this now, I know, filtered to 2 for minimum 2 peaks in a row and minimum 2 isotope peaks per isotope pattern, and MS only. Then you can see what happens. So from my previous 15,000 features, I reduced this now to 2,700. And
what is the isotope information that it takes now?
so the basically collapsed isotope patterns we got through this isotope peak grouping, right? It basically tells you that like a feature contains of multiple features actually, which belong to different isotopes.
This is like retained.
Yes, this is retained.
Because you threw them out. That's why I was wondering how
it did not throw them.
Information if you throw them out.
It did not throw them out. It grouped them together. So it's also
okay.
It's called grouper. Yeah.
Okay.
So this information is retained, and for some other applications like Sirius in silico annotation, we actually rely on this information downstream to also make use of the isotope peak pattern as a qualitative information. So anyway, you can see that we had a massive reduction. And when I now scroll through the peak list from the filtered one, I should basically observe more high quality features. So especially at the lower end, the spiky peaks we observed before are not present anymore. Okay. So now basically the feature finding is done. I can now treat also gaps. So imagine when you have, for example, retention time shifts, then, I mean, right now we used very relaxed parameters, but if we would have more stringent parameters, then eventually of a shift, 2 things are like not aligned correctly, hence they get split. So then kind of like the same compound would be in both samples, but they would have been like separated in 2 features. So this would be a missed peak or a gap, or sometimes maybe just like our threshold was like too strict and there was like a lower abundant compound, so maybe we missed that. So those gaps, when you like go to this peak list, you can kind of like see them, because yeah, here there's like a high abundant feature which seemed to be like present in all the samples, but then there's like in this sample here's a red dot, right? So that means red, there was nothing detected. So what we can do now, after we have like this process table, we can use this XICs as a kind of frame to recheck the raw data with like a little bit like relaxed parameters. So and this is called gap filling. So this is an optional step, and we are aware that this also adds a lot of noise to your final data table. But I guess it's useful to actually take this, especially the split features, into account. So to do the gap filling, you go to peak list methods and then gap filling, and you use the peak finder model. And then, I don't know, you can allow like an intensity tolerance of maybe like 10%, and then also 20 ppm mass accuracy. And normally this is the point where I use like a little bit relaxed retention time settings. As we used already 0.2, I would not probably go much above that, but so we can immediately now run this. And yeah, when you have a lot of features, this is a very time-consuming step as well. But with like strict filtering upstream, it definitely makes this faster. Okay, so now if I open the gap filled table, now let's check what happened with this red dots. Yeah, so as expected, this has turned yellow now. So green means there was a feature, red means there was no feature, and if it's yellow, then it says there was a gap, and now it's gap filled. And that actually, as you can see, happened for a lot of dots. So there's a lot of yellow dots now. So what I would typically recommend you to do is kind of like assess that, maybe export both tables and try how this influences your stats downstream. Okay, in order to make use of this data, you would basically want to bring this into like a sample matrix to export it. Once you're happy with it, you go to peak list methods and then export CSV file, and then I can just here under file name select the folder. So here's the tutorial for today. Close test 2, and now I can select here the different rows I want to export. So the minimum information you will need is the row ID. This is really important because this is the identifier which connects the feature to MS2 spectra in the MGF file we will export in a second. Then, of course, you want to export the mass and the retention time. And then for each sample, you want to export the area under the curve, peak area. And then you hit OK. And then it should write a feature table as CSV file. And now we want to export also the MGFs, so the an MGF of the MS2s we connected to the features. Therefore, we go again to export and then export for GNPS. And here again we select the file or a file name. So it would be to just. And then I have to select the correct mass list I specified at the beginning. Just click on choose and then it's this one. And then you can hit OK. And now you're basically done. So what I would recommend you as well after this, or even somewhere in between, is to save this entire project. Because if you figure out now, okay, there was a problem with some of the processing and I want to change some parameters, you don't have to do all this again. You can actually just save this, and then you can just continue at where you left. So if you go to project, save project as, and then specify. Okay. And then save. I'm not doing that. I already saved it. and then you're good to go. Now, when you want to have a look at what we actually got out of it, we can now open the files we created. So I go here to test 2. I can open this with Excel, and then basically this corresponds to this table I previewed already in MZmine, and yeah, it gives you here row number, mass, retention time, and then the areas under the curve for the different samples. So here the header, you see all the different samples. And then according to this row number, I will get MS2 spectra in the MGF. So this I can, for example, open with Notepad or so. And then, yeah, you can see basically here, MS2 spectra with the ID 2 was from mass 184, so that corresponds to the mass here. And if I scroll further down, you can see here ID 6 is 186 and so on. So here, that's basically our link. And now we can take these files and throw them into GNPS, which Ming gonna show you.